Morning, guys. Cold today, huh? Snowing? Oh my God. Oh man. Okay, let's see where we're at. All right. So you guys made it in the snow. Very good. I figured most people would stay home and watch the lecture on Zoom since of the snow. But it's good you guys made it in. All right. All right. Okay, let's go ahead and get started. It's 9:30. So I got a lot of announcements today. The first announcement is ECE 5106. If you want to continue on with this material and study the second half of the book, then make sure you register for that. All right, it's going to be just like this course. It'll be a lot of fun. In that course, we're going to learn a lot about guided waves and numerical methods, method of moments, and geometrical theory of diffraction and so forth, and Green's functions. And what we've learned in this course so far is how to calculate the radiated fields or the scattered fields due to current distributions that are known, right? And we've come up with some ways to approximate these current distributions, such as physical optics or using some other approximations or surface equivalence theorems, for example. But once we've obtained the current distribution, then we know how to calculate the electromagnetic field due to that current distribution. But there are numerical ways to find the exact current distribution for any geometry and any number of scatterers. And that is a very powerful method called the method of moments based on solving integral equations. So that we'll learn in the next semester. So if you want to continue on with this material, which I suggest you do, please register for that course. Second thing is the spot evaluations. Please fill those out. They're very, very useful for my reviews and also for me to learn what went well in this course and what didn't. So please fill those out. It's very, very important. The other announcement is there's a homework number 7. Your final homework is out now. I suggest that you start it now because the very last problem on the homework is going to be somewhat of a lengthy derivation. So it's very straightforward though. The steps are clear exactly what to do. You just have to go through the pages of the derivation. But it's a very useful derivation, and I'm sure you'll use these examples in your research. They provide analytical solutions. The good thing about analytical solutions that you're studying right now is you can use them to validate your numerical codes or some other research or some other problem you're trying to solve, right? It's always good when you derive a solution or when you write a computer program, you want to make sure that you have the correct program or you're solving the problem correctly and you're getting the right solution. And one way to do that is to sort of test limiting cases or geometries that are known with analytical solutions. So we're learning all of those now. All right, very good. That homework will not be due until the day of the final. It says on the top of the homework, so you can check. That's like a week and a half away, right? So start the homework now, I suggest. It'll be probably the most useful homework you'll do. All right, let's see. So we have only this lecture and 2 more after this, and then we're done and the final, right? So I'll talk more about the final later on, but you'll want to finish this last homework because there will definitely be some things on that homework on the final, right? So you can basically use, okay, yeah. So make sure you do the last homework, all right? And the extra credit if you want to get some extra points. And you'll know your grade because there's no curve, right? It's based on straight points. I put the formula in the syllabus. You can calculate your grade immediately. And if you want to add the extra credit, you can if you choose to do that, all right? Very, very good. Okay. So we looked at scattering from cylindrical objects. We had an axis of symmetry. So it was a 2-dimensional problem. It was an invariant in and out of the board. And we had cylinders of cylindrical shape, I suppose, that were illuminated by plane waves and line sources, right? Those were all conducting metallic. We looked at normal incidence, if you will, and oblique incidence. And we even saw a demonstration where if we illuminate sort of a cylindrical metal rod with a laser pointer, then we can actually see this scattering cone being generated. All right, so it's always good to see something tangible that the math predicts. All right, very nice. So now let's look at plane wave scattering by dielectric cylinders. So what is the problem? We have a dielectric cylinder here. The axis of symmetry is the z-axis in and out of the board. We have the xy plane here with the cylinder of radius a, which exists within it. And it's made of materials with epsilon r, mu r as the permittivity and permeability. It's suspended in free space of epsilon naught, mu naught. And we're illuminating this dielectric cylinder with a TE to Z uniform plane wave now. Before we did TM to Z, right? TM to Z, we have the electric field in and out of the board, and there's only one component. Here we're doing TE to Z, meaning the electric field is transverse to the Z-axis. Therefore, it has no component in the Z-axis or in the Z direction. And since it's a plane wave, the magnetic field must be in the Z direction. So we have the incident electric field now polarized along the Y axis. All right. So it's a plane wave illuminating a dielectric cylinder, traveling in the plus X direction, all right? Okay, what do? Well, we expand all the fields in terms of our cylindrical harmonics or our cylindrical modes, and we apply boundary conditions. We match modes. We calculate the unknown coefficients. So for what are we going to choose for the incident? Okay, so we're going to construct the problem in terms of the magnetic field. And the reason is the magnetic field only has one component. It's easiest to work with, right? We'll obtain the electric field components using Maxwell's equations. So let's work with the magnetic field. The incident magnetic field has some amplitude, H naught, complex amplitude. It's in the Z direction, and we expand it, or we represent it in terms of an expansion of cylindrical wave modes. In this case, J to the minus N Bessel function of order N beta naught P, beta naught because it's in the exterior region, which is free space, and E to the J and phi. This we've already studied. This is the cylindrical mode expansion of a plane wave, right? But now we're expanding the magnetic field in terms of it, in terms of these expansion functions, right? The scattered magnetic field has the same form. We want it to be the same form so we can match modes, right? The form is the same, but here we have traveling waves instead of standing waves. Okay, so these waves represent the plane wave, but these are traveling waves that are, and we're assuming that the waves scattered outward, right? So Hn2, beta naught, rho, because it's in free space, unknown coefficients An. And now we have a third expansion because it's a dielectric medium. So we need the fields within the dielectric region, right? We know the fields within the dielectric region are going to form standing waves because they're going to reflect off the discontinuity back and forth multiple times. So the field, the magnetic field in the dielectric is a general expansion for standing waves. We know for standing wave solutions in cylindrical coordinate system, we have Bessel order 1 and Bessel order 2, Jn and Yn, right? Or not order, rather, kind. So Jn plus Yn with Bn and Cn is the coefficients, and E to the J and phi. And the region of the domain of that expansion is within the dielectric medium alone. Yeah? Okay. So I've repeated these expansions at the top of the slide. Now we're going to calculate the electric field using Maxwell's equations, using Ampere's law from the magnetic field in the Z direction. So if we use Ampere's law, we can calculate, if we only have a Z component of the magnetic field, what components of the electric field we get, and we get E rho and E phi. All right, that's directly from Ampere's law. Okay, so let's perform the calculation. E rho incident is the phi derivative of Hz plus these coefficients. So here are the coefficients. And then we take the derivative with respect to phi of our expansion for H incident. And that means that Jn comes down, right? The derivative of E to the J and phi is Jn E to the J and phi. So we have an N here and then a J, a plus 1 to the exponent on J gives us Jn, all right? E rho scattered is the same thing, but we differentiate the scattered field. So we have a Jn that comes down. And E rho dielectric is the same thing. We differentiate with respect to phi, a Jn comes down, all right? Now, E phi, we have to differentiate with respect to rho. So we have E phi incident. We differentiate H incident with respect to rho. We include a dash here, or a prime, right? That prime indicates, remember, that we're differentiating with respect to the entire argument of the Bessel function, all right? Okay, same thing with E phi scattered. We have Hn2 dash, or Hn2 prime, and E phi dielectric, we have Jn prime and Yn prime, all right? Remember, these have beta 1s in them, not beta naught. Okay. Since the fields must be finite within the dielectric cylinder, why? Because within the dielectric cylinder, we include the point at the origin, rho equal to 0. The fields have to be finite there, right? So we automatically know immediately that Cn is equal to 0. So Cn's are equal to 0 and we have only B and Jn. Yeah? All right. Good. So now we apply boundary conditions. All these problems are just like this. We write the field expansions in terms of the cylindrical or spherical modes in each of the regions, and then we apply boundary conditions to find unknown coefficients, then you're done. Pretty powerful approach of what you're able to do with it. So matching tangential components is the first, or the boundary condition that we have to do here, right? Before we said tangential E has to go to 0 when we were working with conducting cylinders, right? Now we have tangential components of E and H must be continuous. So remember, what you need to remember in this class, you need to remember all of it, right? But if you leave here with a solid understanding of the boundary conditions, then that will be a useful thing, right? Because every problem we've been solving ends up being applying to boundary conditions, right? Here we are again doing it. So tangential components of E. E phi is the tangential component, E rho is normal, and EZ is also tangential, but we don't have EZ. So E phi incident plus, this is wrong. Let me fix that later though. E phi incident plus E phi scattered evaluated at rho equal to A. That puts you on the surface is equal to E phi dielectric evaluated at rho equal to A, right? Okay, so we write E phi incident, we evaluated at A. So here we have E phi incident evaluated at A and E phi scattered evaluated at A. That's equal to E phi dielectric evaluated at A, right? Okay, so we have the summation. Each of these modes are summed from minus infinity to plus infinity. We can factor out the summation sign, if you will, and we'll have a summation of something is equal to a summation of the same summation over the same indices of another thing, right? So that means that has to be true for all n, and therefore what you're summing, I guess what you're summing has to be equal, right? You understand what I'm saying, right? So summation of something is equal to the summation of something else. If the only way this can hold for all n is if this part is equal to this part, right? Because each of these terms aren't you can't add them together, or I guess you can add them together, but they are linearly independent. Okay, so you get this expression here, right? All right. Now, if we multiply through by epsilon over beta, then we get this expression. And if we then write it in this form where we have hn2 prime here, we move this term to the other side and move that one that way, we end up with this expression here. This we call expression 1. All right. Now, this is the mistake that I was trying to say. This should be hz, this should be hz, and this should be hz, right? We only have z components of h. So that was a copy paste error. Okay, so hz incident plus hz scattered at rho equal to A is equal to hz dielectric at rho equal to A. So we write out the equality in terms of the expansions for the z component of h, and we end up with this expression here. All right, that's equation 2. So what do we have here? We have two expressions. We have an is unknowns and bn is unknowns, and we have an is unknowns and bn is unknowns here, right? So now we can solve. We can solve for those coefficients. So I've repeated equation 1 and 2 here at the top of the slide. And if we multiply 1 through by jn beta 1a and 2 by the square root of mu r over epsilon r jn prime beta 1a, then we get the following expression. Why do we do that? Because we want to be able to subtract these two equations and solve for one set of coefficients, say an. And to do that, we need to eliminate the bn's. All right, so in order to eliminate the bn's in these two expressions, we need to make these two terms equal, right? So that when we add the two equations, subtract them rather, that those terms cancel out. So the first equation has square root of mu r epsilon r bn jn prime, and the second one has bn jn beta 1a, right? So if we multiply the first one by this term and the second one by that term, and then add them together, we'll eliminate the bn's, yeah? All right, two equations, two unknowns, that's all it is. Okay, so doing that, we end up with the equation. Okay, so when you multiply through, you get equation 3 and equation 4, then you subtract those two, you get this expression here. And from here, you can solve for the ANs, and these are the ANs. Notice these are constants, right? They have to be constants. So why are they constants? Because each of these functions are evaluated at some point, the surface of the cylinder, right? So, but they're dependent on n because the order of the cylindrical modes, the Hankel functions and the Bessel functions, depend on the index n. So you're adding up a bunch of constants. These are the constants that appear in the expansion of the scattered field, right? So we could plug that back into the scattered field now. Oh, Okay, we need to solve for Bn. So we do the same thing, but now we try to eliminate the Ans, right? And the way we do that is multiply the first one by Hn2 beta naught A, and the second one by Hn2 prime beta naught A, right? So these two terms are now the same. And then when you subtract them, you eliminate the Ans, and you end up with an expression in terms of Bn only, and you can solve for Bn. Again, this is a constant, right? These are all evaluated at a particular point, rho equal to A. Okay, good. So now we have An and Bn, and we can plug those back into the expressions of the expansions that we had. So here are electric fields. We have E phi and E rho, incident, scattered, and dielectric. And these were all in terms of these coefficients An, Bn, and Cn. We know that the Cn's are 0, right? Because the fields have to be finite at the origin. We solve for Ans, we solve for Bn's. Now we know the full form of these fields. Yeah? Okay. Now, these coefficients are in terms of derivatives of the full argument of a Bessel function or a Hankel function, right? So I put here how to do that differentiation if you write a computer program, all right? Which you'll probably do for your homework. So if you want to differentiate with respect to an entire argument of some Bessel function, some cylindrical wave function, Z stands for either J, Y, H1, or H2, okay, of order P. So Z is a general variable here, or general function. D by D alpha X of ZP alpha X. Well, the way you do that is you use this formula here, all right? It's minus ZP plus 1 alpha X plus P over alpha X ZP of X, all right? So if you want to differentiate either a Hankel function or a Bessel function, then you have to add together two different Bessel or Hankel functions with different orders, right? So this is the formula to do it.
For the minus 1 case.
What are you saying?
If we have plus 1 or minus 1 or whatever would be good.
Yeah, you want to probably make this a positive. It will work, right? The minus 1 and plus 1 order of Bessel are related. They're linearly dependent, right? For integer orders. Okay, yeah. There's another formula you can derive where it's P minus 1 and P. All right, if you look in the back of your book, you can correlate that to this. All right, good. So I've gone ahead and worked on this over the last week during the Thanksgiving break and made these examples. So here's an example. Epsilon R is 3.5. The incident magnetic field amplitude is 1 amp per meter. The radius of the cylinder is lambda naught by 2, so the diameter is lambda, and the frequency is 10 gigahertz. And I've taken these expressions on the last slide for E phi, these coefficients. So E phi, scattered. So we'll be looking at the total field, but incident, scattered, and dielectric for rho, phi, and Z. Here are the coefficients. I wrote a computer program, and I made a plot of what MATLAB or what the analytical mathematics predict, right? But what I'm plotting here is the total field. So E phi total is incident plus scatter plus dielectric. And remember, dielectric is 0 outside of the cylinder, and it's non-zero inside. And E phi incident and scattered are 0 inside the cylinder and are non-zero outside. So when you add them together, you kind of piece together these two regions. And E rho total is the same thing. You add them all up. And what I'm plotting here is the magnitude of the total electric field vector, which is the square root of E rho squared plus E phi squared, the total fields, right? So I plotted that here, and we get this expression or this plot. Here, I ran the same simulation in COMSOL multiphysics, and we get the same expression, right? Because after I wrote my computer program, I went to plot this, and I was like, how do I know I got the right answer? Did I make a mistake in the code? Did I do a mistake in the derivations? Did I plot it correctly? So the way I checked that is I went to COMSOL and did a simulation and verified. So it's kind of funny to use an analytic solution or use a numerical approach to validate your analytic solution, because usually it's the other way around. You write a code to do a numerical solution and use your analytic solution to validate it. But either way, they both check out, right? So these analytic solutions are very useful because they allow you to validate programs you write. All right, so you get the exact same thing. This is a fully numerical approach, right? This is a finite element method. This is an exact series expansion solution. This is the analytical solution, right? Good. All right. Very nice. So that's what a plane wave looks like when it scatters off of a dielectric cylinder. We still have a shadow region in the back. We still have a standing wave in the front. But now we have some fields inside the dielectric, right? There's still some contrast. Epsilon R is 3.5 inside and 1 outside. So there's a reflection coefficient and a transmission coefficient. All right, good. So here's the MATLAB code I wrote. I gave it to you guys. You'll probably refer to this when you write some codes for your homeworks. But I'll let you go through this, right? Yeah, you can go through this. The code is there that I used to make those plots. Just scattering from dielectric cylinder, all right? Okay, let's do one more really cool example. Plane wave scattering by a dielectric coated conducting cylinder. So now we have two interfaces, two boundary conditions, right? We have a PEC cylinder here of infinite conductivity with radius A, which is centered at the origin with its axis in and out of the board. And we have a dielectric coating, right? So there's another dielectric cylinder of radius B, which, but it's sort of a hollow cylinder, right? It goes from radius A to B, epsilon R mu R, that coats the dielectric or the metallic cylinder, all right? Okay, so we have now a TM to Z plane wave incident, meaning the electric field is transverse. No, the magnetic field is transverse to the Z direction, meaning that it's in the plane, and the electric field is in and out of the board now in the Z direction. It's traveling in the X direction in free space, and it's incident normally upon a lossless dielectric circular conducting cylinder of radius A. Or, oh no, see. So it should say a lossless dielectric coated conducting cylinder. We can expand the fields within each region in terms of cylindrical wave modes. So we do the same thing. We have the incident electric field. We use our cylindrical wave expansion of the incident plane wave, j to the minus n, j n beta naught rho, e to the j n phi. Why do I have a minus j to the minus n? Well, okay, so you probably haven't done homework on this yet. The last lecture, why is it j to the minus n? All right, yeah, you probably haven't studied it or gone back and looked at it. J to the minus n is the expansion for a plane wave traveling along the positive, say, x-axis, right? If it was j to the plus n, then it would be traveling along the negative x-axis. All right. The scattered field, we expand into similar modes, but we know that it's a scatter field traveling outward from the cylinder. So it's HN2. It's in the free space region, beta naught. And then the dielectric electric field, the electric field within the dielectric will be expanded in terms of standing wave solutions, Jn and Yn. All right? Okay. So I've repeated the expansions here at the top of the slide. Now we use Faraday's law to find the magnetic field components. These are the expressions. We have only an EZ. We need to find H rho and H phi. We do the differentiations. We get very similar expressions as we did for the dielectric cylinder, right? So we end up with prime, Jn prime, Hn2 prime, Jn prime, Yn prime, and we have n times j coming down, Jn, Jn, right? Very good. Okay, of course the coefficients are different. There's a mu instead of an epsilon. You can use duality to kind of obtain these expressions as well. We know that the fields within the dielectric cylinder must be finite everywhere, so Cn coefficients have to be 0. So we know immediately that Cn is equal to 0. Okay. So now we have different boundary conditions, right? We know we have a boundary condition at the conducting cylinder interface, which is at rho equal to A. So we have EZ dielectric at rho equal to A, because that's the expansion inside of the dielectric region, right? Has to be 0. Tangential E goes to 0 on the conductor at rho equal to A. So we take the expression for EZ dielectric and we evaluate it at rho equal to A. So you can see beta 1A, and we set that equal to 0. Okay, in order for this summation to equal 0 for all n, then the argument has to be equal to 0. So Bn, Jn plus Cn, Yn. We know Cn's are 0. Or no, Cn's aren't 0. Did I say that on the last slide? Sorry, that's a mistake. That's a copy over. Yeah, because the origin is not included, right? It's a conducting region. There's no fields there. So this is wrong. Copy and paste again. Okay, so Bn and Cn. So Cn is equal to negative Bn Jn beta 1a over Yn beta 1a. Matching tangential components of the electric field at rho equal to B leads to the following. We have EZ incident plus EZ scattered at rho equal to B is equal to EZ dielectric at rho equal to B. This is the boundary condition for the tangential electric field continuity. So we take the expansion for the incident electric field, the expansion for the scattered electric field, evaluate them at rho equal to B, and set that equal to the expansion for the dielectric electric field, evaluated at rho equal to B as well. All three of these arguments have to be equal to each other, and we get this expression here. We know what the Cn coefficients are in terms of Bn, so we can immediately eliminate the Cn's. And then we'll be left with an expression in terms of An and Bn only. So that's this expression here. We have An's, and then we have Bn, but this is the expression for Bn, right? So this is the right-hand side. So Bn factors out. We have Bn, Jn, beta 1a, or beta 1b. And then we have Cn times Yn, but Cn is negative Bn, Jn, Yn, right? And then we have the Yn. Okay, and then that's equal to, so what you do here is you multiply through, or you make a common denominator, right? So you multiply this term by Yn. Okay, so you're gonna do a lot of this in the homework. This step, you really gotta pay attention to because it's how all of these coefficients simplify. And I know the problem number 5 on your homework that you just got, which is the dielectric sphere. We just did the dielectric cylinder. You're gonna do dielectric sphere. That's a tough problem. It's not a tough problem, but it's a lengthy problem. It's straightforward, right? You apply it, you expand, apply the boundary conditions, but there's a lot of derivation, a lot of algebra. It will involve Legendre polynomials. Here, though, you want to form what's called the Wronskian, right? We've seen that a few times. So the way you do that is you make this a common denominator. So multiply this by Yn beta 1a, and you divide it by Yn beta 1a. Then you have Yn beta 1a times Jn beta 1b minus Jn beta 1a times Yn beta 1b divided by Yn beta 1a as the common denominator. The reason you do that is this numerator is now a Wronskian. All right. Okay. Let's see here. Maybe not Wronskian yet, but that is a common step. Let me see what, oh no, it's not a Wronskian, I'm sorry. Okay, so we did this, but this, we'll see that we're gonna do something exactly similar to this. This doesn't involve any derivatives. You need the derivatives to construct a Wronskian. One of them is differentiated in each term, all right? So, okay, ignore what I said about the Wronskian until later, but make it a common denominator anyhow. And then we're gonna call everything in this bracket here, we're gonna call it Fn, and you'll see why. So we have Bn times Fn here is equal to Jn to the minus n, and we throw this to the other side and throw this term to the other side. And we have this expression. Everybody see how we got that? Okay, good. Why are we making it Fn? Because we're gonna end up with two equations that look exactly. Remember we in the last problem that we solved, we had the dielectric cylinder, we had equation 1 and equation 2, right? We're gonna get the exact same two expressions, the same form, equation 1 and equation 2, and then we can solve it by similarity. So this is equation 2. We're gonna call it equation 2. So we have Fn. Remember, let me show you. Here's our equation 1 and 2. We have An Hn, beta not A, minus Bn times something. In this case, it was Jn. But in the new problem, we're calling it Fn. And then equal to minus J to n j to the minus n jn, right? So remember that. We go here. We have the same exact equation, an, hn, bn times, it was jn, but now we're calling it fn, where fn is all of this, all right? This is fn, minus is equal to minus j to the minus n, j, and beta not b. So we almost have we do have the exact same equation. Now we're going to match tangential components of the magnetic field at rho equal to b. The tangential component of the magnetic field is h phi. We match those at rho equal to b, and we write the expression for h phi incident plus h phi scattered. We evaluate these at rho equal to b, and we set that equal to h phi dielectric evaluated at rho equal to b as well. In order for these summations for all n to be equal, their arguments must be equal. So we have this this equality here. And using the result for the coefficients of Cn in terms of Bn, which we derived by using the tangential electric field goes to zero boundary condition at rho equal to A, then we can plug in for Cn right here. Bn minus Bn times this was Cn, right? And now we have square root of epsilon r because beta 1 over beta naught. The only difference between those two is a square root of epsilon r. Okay, in this derivation, I'm assuming that mu r equal to 1, all right?
Is the summation equal to a lesser summation? Is it possible for index terms to be remapped to the equality holds on different coefficients when it's summed up, but the individual coefficients are not equal to each other?
So the whole point of the terms of this summation is they're linearly independent. So you can't really mix them, right? If you want these summations to be equal for all n, then the nth term of this summation has to equal to the nth term of this summation has to equal to the nth term of this summation, because the n plus 1 or any other n term cannot cancel or cannot contribute to the equality for the nth term, because it's like x squared and x cubed, right? They don't, you can't use them to, you can add them together, but they can't cancel each other out. They're linearly independent, right? Okay. So we get the following expression. Now we're going to define, so we do the same thing, common denominator, and here we call this Gn, all right? And we end up with equation 1. Now this equation 1 is exactly the same as the equation 1 for the dielectric cylinder. So we have this equation 1 and this equation 2. And these, if you compare them to the previous problem, were exactly the same form. All right? So here's the equation 1 and equation 2 from the previous problem. And if you compare the two, the only thing that's different is, okay, so here's equation 1 from the previous problem, equation 2 from the previous problem, here's equation 1 from the current problem, and equation 2 from the current problem. And if you compare them, we can use the previous solution that we derived, the coefficients, by making the following changes. Here's B, here's A. So A goes to B, mu goes to, okay, so the mu is equal to 1 in this problem, but mu goes to epsilon, epsilon goes to mu, Jn prime goes to Gn, and Jn goes to Fn. All right? If you make those changes, then you can just rewrite An, Bn, and Cn from the last problem, but you replace A with B and mu with epsilon, epsilon with mu, and Jn prime beta 1a with Gn, and Jn beta 1a with Fn. All right? So here are now the coefficients An, Bn, and Cn for the dielectric coated conducting cylinder problem with mu r equal to 1. All right? So now that we have the coefficients, they're a little more complicated, right? Because they look very similar, but we had these functions Gn and Fn in them. And we know that Gn and Fn expand out into more constants, right? So Gn and Fn, here's Gn, right? So this is the definition for Gn, and then Fn's on the previous slide, right? So you have to replace these G's and F's with the G's and F's with the previous expressions, right? Okay, so we have the final solution, E incident, is Z naught or Z hat E naught J to the minus N. So this is the incident electric field, doesn't have any coefficients, right? The scattered field has the ANs. We know what the ANs are now. And the dielectric fields have BNs and CNs. Here is the CNs, here are the BNs. Yeah, so we solved the problem. All right, it's a tough problem. I mean, it has very nice symmetry, so you can obviously apply boundary conditions and use your field expansions. That's why these problems we can solve this way by mode matching because of the cylindrical symmetry, right? But it's kind of a complicated problem. If you think about it numerically, you have a dielectric coating on a conducting cylinder. There's a lot going on, right? When you illuminate it with a plane wave.
You have like the layered dielectric of kind of infinitesimally different dielectric layers in the great sphere.
Say again?
Like if you have the layered dielectric, they solve the Green's function and they do the shells around the dielectric.
Okay.
Would this still be a way to sort of make it so it kind of sequentially builds on top of each other?
Yeah, so you're talking about solving for a Green's function of this structure, right? For a Green's function, you have to place a source somewhere, like a delta function, and solve for the scattered field everywhere. Yeah, it's possible for sure. You can make a Green's function for these in terms of modal expansions and matching coefficients. You can do that. Okay, good. All right, now we're going to do scattering by conducting wedges. So before we had the boundary conditions for the cylinders at rho equal to some constant value, rho equal to A, rho equal to B, right? But now we're going to look at a different kind of boundary condition in terms of the angular variable phi instead of the radial variable rho. So we can have interfaces where at phi equal to a constant and phi equal to some other constant, right? Instead of rho equal to a constant. What that forms is called a wedge. So these planes, they go out to infinity, right? So it's an infinite wedge. And the boundaries are at rho equal to some constant here, say rho equal to alpha and rho equal to 2 pi minus alpha. Yeah. All right, so this is another kind of problem that we can solve using cylindrical modes. So rather than having boundaries defined by constant rho, we can also have boundaries defined by constant phi. In this case, the structure is called a wedge. The scattering by a conducting wedge solution is very important in the development of geometrical theory of diffraction that we're going to study next semester. The way geometrical theory of diffraction builds up the theory is it solves what are called canonical problems, all right? And it uses the solutions to the canonical problems to solve diffraction problems or for general geometry. And one of the canonical problems is the scattering by a half plane, all right? And this wedge reduces to a half plane when alpha goes to 0. All right? Okay, so let us assume that an infinite electric line source of electric current IE, which is here, located at rho prime and phi prime, illuminates, is placed near a conducting wedge whose total inner wedge angle, WA, is equal to 2 alpha. So this is the total wedge angle here, which is 2 times alpha. All right? The incident field in the absence of the wedge, remember the incident field is omnipresent in the absence of the scatterer, can be described using the addition theorem for Hankel functions because the line source is displaced from the origin, right? So we have to use the addition theorem for Hankel functions in order to represent the electric field. So we're going to have an inner expansion and an outer expansion for the incident field due to the line source. All right? So the line source fields can be found from negative beta squared I naught over 4 omega epsilon into H naught 2 beta rho minus rho prime magnitude. Because the only thing that matters is the distance from the source to the observation point, right? So we can represent this in terms of the law of cosines, and then we can expand inner and outer expansion using ensuring reciprocity holds and continuity at the source. So we get this expression, right? We derived this before. So what we have here is an inner and an outer expansion. The inner expansion remember, this is reciprocal, meaning we can exchange rho prime with rho and phi with phi prime, and we get the same result. And it is also continuous at rho equal to A and phi equal to phi prime. So in the inner expansion, we have Jm beta rho and Hm2 beta rho prime. In the outer expansion, we have Jm beta rho prime and Hm2 beta rho. All right? Okay. In anticipation that the Z component of the total field, because we're applying the boundary conditions to the total electric field, must vanish at the faces of the wedge at phi equal to alpha and phi equal to 2 pi minus alpha, and satisfy reciprocity as well. Interchanging source and observation points gives you a symmetric result. And that the phi variations form standing waves that bounce back and forth between the plates forming the wedge. Okay, so that's kind of hard to imagine, right? So normally you're used to standing waves between two parallel plates. If I have a wave traveling, toward this parallel plate, it reflects and goes to another parallel plate and reflects from there, and you form a standing wave in between these two things, right? But these are Cartesian wave functions, meaning they travel along the x, y, or z axis, right, as exponentials. Now, here we have cylindrical mode functions that are a function of the azimuthal variable. So you can imagine if I have a wedge like this, let me draw it. If I have a wedge like that, then I have some wave which is traveling here, reflects, goes back, and travels like that, and then it continues, right? So these are cylindrical mode functions, or azimuthal functions, right? We have radial functions, azimuthal functions, and z-directed functions. So these azimuthal functions are going to bounce back and forth between the two faces of the plate, two faces of the wedge, right? So we expect there to be standing waves in phi. All right, well, okay. We can write the scattered field then as standing waves in terms of phi. So here's the phi variation. Sinusoids are standing waves, right? We can have reciprocity says that we include F and G. And we know, first off, we know we have traveling waves in the outward expansion. So this is the outward expansion, right? Or outer expansion. This is the inner expansion. We have traveling waves in the outer region. We have standing waves in the inner region, right? That we know right away. And we know we need to satisfy reciprocity. So we need to have some unknown function F and some unknown function G here of the prime coordinates, right? Okay. And we know we have standing waves in the phi direction. So that's how we constructed these solutions. All right. The fields must be continuous at rho equal to rho prime. We know that. So that means that the inner expansion here at rho equal to rho prime has to equal to the outer expansion at rho equal to rho prime, right? Okay. So we set those equal to each other. The sinusoids cancel out, and we have f of rho prime j nu of beta rho prime equal to d nu g rho prime h nu 2 beta rho prime. In order for these two expansions to be equal, or this equality to hold, a nu has to equal to c nu. We can call it d nu, or we can call it a nu. F of rho prime has to equal to h nu 2, and g of rho prime has to equal to j nu beta rho prime. So that if you satisfy these three equalities, then this expression becomes reciprocal and continuous at rho equal to rho prime, and forms standing waves in the phi direction, and that's it. Remember, we're talking about the total field here, though, which is the incident plus scattered. So we're expanding the total field in terms of, it's the total field that has to satisfy all of these conditions, right? Not the incident alone or the scatter field alone, the total field. Okay, good. Well, the total field has to satisfy the boundary conditions as well. So here's our final solution for the total electric field. We have a symmetric result now, so it's reciprocal, right? It's reciprocal. The phi variations form standing waves, they're sinusoids. And now we can apply the boundary conditions easily because we expanded the total electric field to find the coefficients. This should not be nu, this should be a nu. A nu, all right? We can find the coefficients. All right. I've repeated the expansion that we have for the total field at the top of the slide. Now we're going to apply the boundary conditions. We know that phi equal to alpha. Okay, so where are the boundary conditions? There are boundary conditions in phi now, not in rho. So in phi, the boundary conditions are at E tangential goes to 0 at phi equal to alpha and at phi equal to 2 pi minus alpha. So 2 pi minus alpha is this face, right? 2 pi minus alpha. So at phi equal to alpha, what happens? When phi is equal to alpha, then this becomes sine of 0, this goes to 0. So the whole expression goes to 0. And at phi equal to alpha, this expression goes 0. So already at phi equal to alpha, the total field vanishes. Now we just have to ensure that it also vanishes at phi equal to 2 pi minus alpha at the other wedge face. So we take these expressions and we set the phi variation equal to each other. So sine of nu, so let's concentrate on the sinusoid here. Concentrate on this sinusoid with the observation variable in it. Sine of nu phi minus alpha evaluated at phi equal to 2 pi minus alpha is this expression. We can factor out the 2 and what we get is this expression that has to equal to 0. So the argument of this sinusoid has to equal to 2n pi, right? So this argument, so sine inverse is 0. Take the sine inverse of both sides. Sine inverse of 0 is n pi. So nu is equal to this expression for m integer. All right? So nu is restricted to take integer values. Nu is restricted to take these values that are a function of the index m, and m is restricted to integer values. All right? Okay. So still, we don't know what a nu is, right? We know what nu is. Okay, sorry. Let me go back to the previous slide. And when I said this was a nu, this is not a nu. This really is nu, okay? So this is not a nu, this really is nu. We found nu using the boundary conditions. Now we still have to find a nu. A nu will depend on the type of source, all right? So for different sources, we're gonna find different a nus. How are we gonna do that? Well, we're going to use Fourier series expansion and take the source to infinity. So I'll show you how to do that. But to do that first, we need to find the phi component of the magnetic field using Faraday's law. We're going to use this in our derivation of these coefficients a nu. So h phi is equal to minus 1 over j omega mu, 1 over rho partial Ez total with respect to phi. And we know Ez total here. We're going to differentiate with respect to rho to get h phi. So that's this expression here. If we differentiate with respect to phi, then something bothers me here. These should be cosine, right? What did we do wrong here? Differentiate. Oh, no. Looks like we differentiated with respect to rho here. H nu prime. Okay, maybe I made a mistake. Let's do the derivation really quick. So, what are we using? Faraday's law. Curl of E is equal to minus j omega mu h. So, h is equal to minus 1 over j omega mu, the curl of E. If we have Ez, I need the expressions. We could derive them really quick for cylindrical coordinates. Well, let's go back. We have them derived already. Somewhere here in the lecture, I know we used them. H phi is differentiation with respect to rho. So yeah, so we gotta make that correction. So this is rho. All right. And is there a minus sign there too? Let's see. I feel like there shouldn't be minus either, and there shouldn't be 1 over rho either. So I think this is gone and that. Okay, let me just double check. So, oops, yeah. If we go here, where was that? Here. So it's 1 over j omega mu partial Ez partial rho, right? So yeah, we definitely have a mistake there. It is, yeah, 1 over j omega mu partial EZ partial. That's correct. Yeah. All right, good. All right, so yeah, you differentiate with respect to rho, you pick up these little primes here, right? All right. Okay. So what are we going to do? Let me see. Now that we have H5, we're going to find the current density, not on the surface of the PEC wedge, but at the source, and you'll see why. So the current density at the source is related to the total tangential magnetic field from J, from the boundary condition, J equal to N cross H total equal to rho crossed with rho hat H rho plus phi hat H phi, evaluated at rho equal to rho plus and rho minus, the difference of those, right? So rho cross rho goes to 0. Rho crossed with phi gives you Z. So we have Z and it's H phi. That's why we only calculated H phi. And we evaluate that at both rho plus and rho minus, which means we subtract the two. So we have Z hat H phi at rho plus. Okay, rho prime, right? Rho prime is here. So rho prime plus is on, rho prime minus is here. And rho prime plus is on just on the other side of the source. So it looks like this. We have the source here. This is rho prime minus, and this vector here is rho prime plus, right? Just on the two sides of the source. Why do we do that? Because the discontinuity, we know the total tangential, or we know the total magnetic field, right? Tangential in this case to the source. We know the total tangential magnetic field. If we can calculate its discontinuity, then we know that the source, J, has to support that discontinuity to the magnetic field. And if we can relate the line source to the current density, we can equate these two expressions and find the coefficients. That's what the strategy is here. Yeah.
The source is like an infinitesimal dipole right at the corner of the wedge. We have to think about the problem.
Okay, so infinitesimal dipole doesn't have the cylindrical symmetry that we're talking about here. Everything's a line source, infinite in and out of the board, right? Invariant in and out of the board. So it would be a line source. If it's placed right at the vertex of the wedge, that would be, you could probably take your expressions and take a limiting value and see what happens there. If it's too close, it might not radiate, right? Well, that's something you can investigate. You know, we have analytic expressions. You can take a look at that to satisfy your curiosity. Okay, so let's take the H phi, evaluate it at rho plus. Okay, so what is this? Rho plus is what? Remember, we did the addition theorem for Hengel functions. So rho plus is the outer expansion, and we subtract from that the inner expansion, right? Because rho minus just before the source is the inner expansion, just after the source is the outer expansion. So here is the outer expansion minus the inner expansion.
Now, rho plus is outward traveling radially.
Rho plus is a location, it's a position vector, it's coordinates, which is just after the source infinitesimally in the rho prime direction, but just after rho prime. Rho prime is pointing to the source exactly, right? The line source is a point, infinite in and out of the board. So rho prime points to the source. If I say rho prime plus, it's just on the plus side of rho prime minus on the minus side of rho prime. That means we're subtracting the inner and outer expansions, right? Okay. All right, so let's see what we do from here. So we take these expressions H, right? We know that HN2 is equal to JN minus YN. So we use that. So we write H in terms of Y and J, and this H in terms of Y and J, and then we can get this expression. All right? Okay, now we use the Wronskian. We have J into Y prime minus J prime into Y. That is Wronskian, right? So the Wronskian gives you 2 over pi times mu. It's some constants, right? We presented it earlier in the lecture, in some slides back, the formula for the Wronskian. But you apply that formula you get this, all right, for the current density at the source point. All right, now, comparing this result to the Fourier series expansion of a current impulse of amplitude, i.e. located at rho equal to rho prime and phi equal to phi prime, this here is the Fourier series expansion in terms of cylindrical coordinates of a impulse, right? In the cylindrical sense, it's a line source. If you compare these two, then you can find what alpha n is, or alpha nu, because the current density here is in terms of alpha nu for our expressions, but this looks a lot like the Fourier series expansion of a line source, an impulse in cylindrical coordinates, which has this expression. Therefore, we can find the coefficients to be this, all right? So that took someone's ingenuity when they were doing the derivation, like, oh, this looks a lot like a Fourier series expansion, but they've had seen a Fourier series expansion in terms of cylindrical coordinate functions for an impulse before, right? To make that connection. So my suggestion to you is don't trip up on how did we get, this is a kind of a leap. It's the more things you study and the more knowledge you gain throughout your research and your career, you'll be able to make these connections, right? So that's the point of taking these courses and stuff. All right. So it looks a lot like a Fourier series expansion that somebody has solved before, or maybe you've seen before too, right? Good. A nu is, okay, so here's an example. I plotted for alpha equal to 20 degrees. So this angle here is 20 degrees, right? And rho prime, the line source is located at rho equal to 2 lambda and phi prime equal to 3 pi over 4. So it's here, right? Rho prime, yeah? And the line source has a current of 1 amp and it's at 10 gigahertz. And I've plotted these expressions for, this is the total electric field, right? This is EZ total. I should have probably put that here. This is EZ total, absolute value. No, real part. So this is the real part of EZ total. All right? Oh, shoot. What? Okay, real part of EZ total. So this is what it looks like, right? We see kind of standing waves here, right? In azimuth. We kind of see an image of this point source, and I think you're going to look at this later in your homework. And you see kind of, so this line source is infinite and out of the board. It radiates in the presence of this PEC wedge of total wedge angle 40 degrees, and it produces this kind of near scattered electric field. All right. Okay, this line source solution becomes very useful when we study GTD next semester, or the plane wave solution. So let's look at the plane wave solution. So let's use the large argument expansion, the Hankel function in the outer expansion. How do we make this a plane wave problem, right? We have a line source which is located very close to a wedge, right? So here's the line source. How can we change this to plane wave excitation? Well, the idea is to take this line source off to infinity. If you take the line source off to infinity, by the time that cylindrical wave gets to the wedge, it's going to be a plane wave. That's a strategy. So let's take the line source and find its large argument expansion with the far field for it, right? So replace the Hankel function with the large argument expansion. It should be beta prime. Let's make sure. So let's see. Here. So the outer expansion is this one. No, it's beta m. So it's rho, it's beta rho. The outer expansion we want the line source, which is located at rho prime though, not rho. So I guess we're gonna use the far field. Okay, so that's kind of confusing. Let's see. So we let beta rho go to infinity. We have this expression. So rho is still at rho prime. We haven't set rho prime going to infinity yet. So this is still the large argument expansion for the Hankel function in the outer expansion. We get the far fields for the line source excitation. Okay, We can then substitute what we know A nu to be for the line source. And we can write this result as FE, everything in front, we're just going to call FE, all right? Oh no, so this is just the far field observation of the scattering from the wedge, all right? We get the far fields for the lines. Okay, yeah, sorry. So it's okay. So this is the far field. If you want the far field scattered by the wedge that's excited by a line source that's very near to it. What is the far scattered fields, right? It's this expression. You just take the Hankel function for the observation point, replace it with its large argument expansion. All right. So it looks like this, right? This is the far field for the line source near the wedge. If we use the large argument expansion of the Hankel function, so this is different, right? This is something separate. This is for the far fields of this problem. The far fields of this problem, right? All right, and this one. Now, if we want plane wave excitation, we do the opposite. We take the, we use the large argument expansion for the Hankel function of the inner expansion because the source, now, if the source point goes to infinity, right? Then the inner expansion is everything because the outer expansion is beyond the source, but the source is at infinity now, right? So if we move the source to infinity, everything's an inner expansion. So we take the inner expansion, we use the large argument expansion for the Hankel function, we can obtain the total field scattered by the wedge for plane wave incidence, all right? So now we're taking beta rho prime going to infinity, makes much more sense. And we call all the coefficients GE of rho prime, which is very similar to this, right? It's the exact same thing, except it's rho prime instead of rho. All right? And we just call all that E naught. So E naught equals to G is equal to all this. So this is plane wave excitation of a wedge. And this is what we're going to use for next semester's geometrical theory diffraction. Plane wave excitation of a half plane when alpha goes to 0. All right, so here is the plot of the far field. Plane wave incidence observed 1 lambda away. So the source at infinity, so it's a plane wave incidence. We observe the field at 1 lambda away from the edge of the wedge. So rho, the observation is 1 lambda away from the origin. All right, this is all wedge. All right, and we have multiple cases here. We have 2 alpha equal to 0. So it's a half plane solution, which is the solid line. 2 alpha equal to 90, which means it's a, 2 alpha equal to 90. Yeah, that means that it's a right angle corner, right? A 90 degree. The observation's at rho equal to lambda, and the source is at 30 degrees, but it's a plane wave incidence. So the plane wave's coming in at an angle from 30 degrees. And what you see here is that the 90 degree and the wedge differ only here, right? The 90 degree in the half plane, the corner in the half plane. Yeah. All right. So you're solving some pretty cool problems here. Okay. So that's all we're doing for cylindrical coordinates. We did planar structures in the beginning of this lecture. We did all of our cylindrical problems. We did a lot of cylindrical problems, right? Did the wedges, we did the cylinders, dielectric, conducting, oblique incidence, normal incidence, TE and TM polarization, and we did a dielectric coated conducting cylinder. All right. Now we're going to do spherical problems. So just like we did with cylindrical mode functions, we had to learn a couple of theorems, if you will, or you know, the addition theorems. We had to learn the cylindrical mode expansion of a plane wave, all of these things. We're going to do all the same thing in terms of spherical modes. All right. So now we're getting into the last topic of our course. Unless we get done fast enough, we'll study some metasurface stuff on the last lecture, all right? Which I think we probably will. But here, we're looking at spherical wave representation of a vertical ideal dipole. Before, first thing we studied when we looked at cylindrical waves was what does radiation from an infinite line source look like, right? And that was our Hankel function, H naught. And then when we displace a line source from the origin, we had to introduce the addition theorem for Hankel functions. All right, here we're going to do the same thing, but in spherical coordinates, it's a finite source. It's not an infinite line source. It's a infinitesimal dipole of constant current. All right, so here we have the XYZ axis, Cartesian coordinate system. We have an infinitesimal ideal dipole located at the origin. And the observation point is at R. Okay, so remember, the observation is always R, unprimed, right? That's this vector here. The source is pointed to by R prime, which is this little vector here, but it's very, very small, right? And then capital R is R minus R prime, right? But R prime is nearly 0. So R is approximately equal to, capital R is approximately equal to little r, right? That's the approximation you use when you solve for the fields due to an infinitesimal dipole using the vector potential approach in lecture 6, I believe, right? Okay, so that's the coordinate system. So remember, when we had an infinite line source, we ended up with H02 when it was at the origin, right? 0th order Hankel function of kind 2 with beta naught rho as the argument, right? So the 0th order of the Hankel functions, the cylindrical waves, represent a perfect cylinder expanding. You remember that? Let me go back here and show you, just so you can remember. That was way back here. The 0th order, H0 2, so here's EZ, here's H0 2 represented a perfect cylindrical wave, right? All right, with no azimuthal variation. Remember, azimuthal variation is linked to the radial variation. So if we have any azimuthal variation, then it cannot be H0, right? And if we have H0, that's the only mode that has no azimuthal variation, because then M is equal to 0 and azimuthal variation goes to 0, right? So we're gonna have something very similar here in cylindrical or spherical coordinates rather. But in spherical coordinates, we're gonna end up with little H0, right? So now you have to remember all of your spherical wave functions. So the z-directed vertical electric current element placed at the origin has this magnetic vector potential. You've solved this before in lecture 6 and in your homework. Z hat is z-directed, mu I e delta L over 4 pi, e to the minus j beta r over r, right? Or 4 pi r, but the 4 pi is there. So that's equal to minus z j mu beta I e delta L over 4 pi H0 2 of beta r, where we're defining H0 2 beta r as e to the minus j beta r over minus j beta r. What is this? Just the Green's function, except for that minus sign in the j and the beta, or there's a 4 pi. It's a little different, right? But what is it? First off, it's only a function of r. So that means you can have no variation in theta or phi. Means everything has to be perfect spheres, right? The amplitude decays is 1 over r. So at different concentric spheres, I have different amplitudes that are decaying with respect to 1 over r. And the phase delays with respect to the radial variable as well. So at different spheres, I have different phase delay. But these are concentric perfect spheres because there's no phi or theta variation dependence in this function, H0 2. So here we are again with H0 2 representing now a perfect spherical wave, which is represented here. These are expanding spheres, right? As the wave fronts of H0 2. Yeah? Okay, we can also use duality to find what the z-directed vertical magnetic current element placed at the origin using its electric vector potential. So we use duality, we get here, right? All right, so if the source is displaced from the origin, then the spherical Bessel function. So remember, when you see these spherical Bessel functions, which are lowercase, they're all related to the capital J or H, right? There's just some coefficients. And there's a reason for those coefficients. The coefficients give you the right decay, right? So you'll see that the relationship between little h and capital H is some kind of square root of 1 over r, dependence, proportionality, right? Because capital H decays is 1 over the square root of r, or square root of rho, whereas these spherical waves have to decay as 1 over r. So you have to add another 1 over the square root of r. You'll see that, right? So anyway, if it's not at the origin, then we can say that H0 2 is e to the minus j beta r minus r prime, capital R and capital R down here. Yeah.
The vector potential R, there's just a magnitude of vector. What's that R vector?
Where? If it doesn't have a vector on it, if it's this is the magnitude of R, yeah. If it doesn't have a vector on it, then it implies the magnitude of the vector R. All right? Okay, so remember though, there's no such thing as a perfect spherical radiation in nature, right? Because radiation comes from what? You can have a spherically symmetric static electric field with a point charge, right? You get a spherically symmetric electric field, but you can never have spherically symmetric radiation because why? Radiation is due to what? What do you need to have radiation? Current, right? Current is accelerated charges. You need time variation, you need acceleration of charges. So current, but current is always directed, right? Current is the flow of charges in some direction. It has to move in some direction. If you have directed current, then in the direction of the current, you have no radiation along the axis of current, right? Because it's only the, okay, so it's maximum broadside. You'll see that when you study antennas. It's called the kink model. So basically by accelerating a charge along some direction, you create what's called a kink in the static electric field that existed before the time of acceleration. And that radiates out like a wave on a rope, right? Or a string. Anyway.
And we have a circular orbit, or if we have.
So in any case, if you have a current, you will not ever be able to generate an isotropic radiation pattern. It's not a solution to Maxwell's equations, so that's for sure out the possibility realm. All right. So we know that the z-directed ideal dipole should have a sine of theta pattern, right? Why don't we see that here? We're saying that this is a function of R only with some constants and coefficients. The reason is the following. This z hat here, right? It says this is z hat directed, but we're going to observe it in terms of theta and phi. Then we know that we have to transform this z hat unit vector in terms of R and theta, which has this expansion here. So then we introduce the sine theta pattern, right? In tangential components. So it does agree with physics. All right, that's the spherical wave representation of vertical ideal dipole. What about zonal? Now we're going to study what are zonal and tessaro harmonics. How can we combine our spherical expansion functions that we obtained through this separation of variable solution of the wave equation in spherical coordinates, which remember we had to construct using the vector potentials and so forth. How can we combine those to expand electric and magnetic fields in terms of? So we have, remember, in the radial direction, we have spherical Bessel, spherical Hankel, which are the lowercase j, lowercase y, lowercase h, right? They're related to the capital H, Y, and J through some kind of coefficient, right? Square root of like pi beta over, or 2j over pi beta rho, something, all right? You'll see in the last lecture. I'll probably remind you in a few slides. In the polar direction, the theta direction, we had Legendre functions, associated Legendre polynomials, right? Which were related to the Legendre polynomials themselves. The associated Legendre functions were related to Legendre polynomials through another sort of expression, all right? So it might help you to go back in and study lecture 3 a little bit before next class. And in the azimuthal direction, we had exponentials and sine function, sine, cosine, all right? But let's combine, let's understand what we can do with these Legendre polynomials. So a Legendre polynomial, Pn cosine theta, forms a complete set over the interval from 0 to pi, right? And are often called zonal harmonics. So here's a zonal harmonic, right? These are Pn's where they have no variation in phi, right? We're talking about the polar variation only, the Legendre polynomials only. So they have symmetry in the azimuthal direction, but they have variation in theta. So they look like this, right? Different types of these things. Any arbitrary function, wave function, can be expanded in terms of these Legendre polynomials over the interval from 0 to pi. All right. 0 to pi. And they have these, okay, so if you can expand any function in terms of these, a summation of weighted Legendre polynomials, then how do we find the coefficients? We better hope that they're orthogonal, right? So it's true. Pn is orthogonal to Pm with this orthogonality relationship here, all right? So if you integrate Pn versus Pm, sine theta d theta, then you get 0 if they're not equal. And if they are equal, n equal to m, you get 2 over 2m plus 1. So these are orthogonal polynomials because you get a 0 when n is not m. And you get, they're not orthonormal because you would get a 1 here when n equals to m, but they are orthogonal, which allows you to expand functions in terms of them as linearly independent bases, orthogonal bases, and allows you to develop a formula to find the coefficients right here. So here, you can expand any function f of theta in terms of a summation of Pn cosine theta with unknown coefficients an. Because they're orthogonal, we can find these coefficients an by using this integration identity or this relationship, the orthogonality relationship, as 2n plus 1 over 2, integrate from 0 to pi, whatever function we have, trying to expand in terms of these polynomials, weighted multiplied by one of these polynomials, the nth one, we get the nth coefficient using this formula. Yeah, this is called a Fourier-Legendre series expansion. All right, so let's end here. We'll come back to this slide next time. And we still have a few more things to get through, of course. And then hopefully we'll finish all those next lecture and we'll be able to get into metasurfaces as our last lecture. As a bonus material, won't be on your final. Oh, yeah. We'll do that too at the last lecture. Remind me again. All right, good. Any questions? Get to your homework. You need to start that soon. It's the last problem's a long one. Not long, but I don't know. Just start your homework. Don't wait till like the day or two before, because I know you're gonna come to my office and try to figure out how to solve it fast. Learn from me. All right. All right. See you guys. Yes. Yeah, we have a lecture on Thursday and one next Tuesday, and then the finals on Friday of next week. All right. So we're almost there. Yeah, you can bring everything you want in the exam. It's gonna be similar to the midterm. You're gonna have one problem that will combine, probably two problems, I don't know. That's gonna combine a bunch of topics so that it's somewhat comprehensive. Oh, no, wait a minute. The final is like 2 hours long, isn't it? I haven't made it yet, but you'll have more problems in the midterm. I think we have 2 hours exam for the final. All right, good. See you guys.
Is it just gonna be scattered stuff or just gonna be like comprehensive?
It'll probably be comprehensive, but representative problems to show you mastered the material that was taught to you the whole course. Yeah, sure. Yeah. What is your maybe we could talk about it now. Do you have? No problem. Have a good one.
Because that's my other subject.
Okay, very good.
Just I figured why not.
Yeah, it's a good idea.
Yeah, I can do it on electromagnetic interference and devices like Cyls.
Sure, that's a good idea.
And can you like tell me any other similar topics I can do?
Interference? Let me think about that. That's not my direct research area. EMI. I'm trying to think of what professor would do that. So it's ways to reduce interference, right?
Yeah. I'm thinking the
I'd have to
course
look.
Dr. Dom.
Oh, really? Ask Professor Don.
Yeah. So should I ask like Professor Dom?
Yeah, tell him that you're doing a extra credit little paper study, and that you want to look at something with interference. If that's his research area, then he'd probably be a much better person to ask, because I don't read many papers on electromagnetic interference. And I'd probably have to like look some up and kind of survey them and think of what would be a good choice. But he might know maybe a fundamental paper in that area, one of the original concepts or something, you know.
I was not sure like how to replace it.
Yeah, whatever paper has results that you can recreate in a timely manner,
redo the derivations, redo a simulation or something. But that might be the,